Let's look at the first example. Under ideal conditions, flies reproduce rapidly. After introducing 4 flies to a contained laboratory environment, the following data was collected. Use the data to algebraically determine an exponential growth function representing the population of flies. Verify your model using technology and evaluate the reasonableness of the model stating the strengths and limitations. So looking at the table, number of flies is N, number of weeks is T. So our formula is going to be, because it says it's an exponential growth function, N equals N0 e to the kt. Now look at the information you're given. The first is the initial amount, because when T is 0, N is 4. Now I could plug T is 0 into that, or you can just realize that N base 0 is the initial amount. So N equals 4e to the kt. Note that if you went T is 0, N is 4, you would have had 4 equals initial times e to the 0k. So 4 equals N0 because of that e to the 0k. Keep going, e to the 0. So 4 equals that initial amount. Okay. Now we need to try and find k. Use the next value in the table. So when T is 1, N is 133. So 133 equals 4e to the k. 133 divided by 4 equals e to the k. Change to a log. K equals ln of 133 over 4. Now, it does say algebraically determine. That doesn't mean it's a tech-free question. Algebraically determine is telling you that you can use your calculator, but you need to do the algebraic steps. Right? So that's the exact value there. I'm going to evaluate what that is, though, to get an approximate. That's approximately 3.50. Now I'm going to verify using the other value in the table. So T equals 2, N equals 4,400. So 4,400 equals 4e to the 2k. Divide both sides by 4. 1100 equals e to the 2k. Go to a log. 2k equals ln of 1100. K is ln of 1100 divided by 2. This is why that technology is helpful, to be able to see what that actually equals. And that two decimal places is also 3.50. So you can see that these values match. Now the question is asking for an exponential growth function. You could use one of the logs and put that into your growth function. We know that they're not identical. Or you can say n equals 4e to the 3.50t. And you could say that that's approximate. If this was tech-free, then you would have answered with one of the logs. Okay, so now let's verify our model using technology by going to our graphics calculators. So we're in lists and spreadsheets. In our first column, we're going to have T. Using our data table, 0, 1, 2. In our second column, we have N. Oops. 133, 4,400. Go to another cell, menu, statistics, stat calculations. We're doing an exponential regression. First, X list is T, Y list is N, and go OK. So you can see that the exponential model is in the form of AB to the X, and it's saying it's approximately 4.00 multiplied by 33.17 to the power of X, and it's giving an R squared of 1, which means it's a perfect model that all the data fits perfectly. So I'm going to screenshot that and go back to our slides. So our model using technology is N is approximately 4.00 multiplied by 33.17 to the T. Now we need to compare that with the model we found algebraically. Now we did find an exponential model E. So we need to grab that E to the 3.50 and compare it to that B. So E to the 3.50 is approximately 33.12. Comparing those two values, 33.17 is approximately the same as 33.12, so the model is verified. So the final part of the question is evaluate the reasonableness of the model stating the strengths and limitations. Okay, so things to think about. R squared is 1. That means it's a perfect model. But we are extrapolating, or we may need to extrapolate. So extrapolating beyond T is 2 is dependent on the conditions. It's not just because of R squared is 1. R squared is 1 is great, but what will happen beyond all the data given to us? If you read the question again, it says in a contained laboratory environment. So that is going to have limitations. It may not have enough resources. It depends on its size. So the model continuing outside the data range is going to be dependent on sufficient nutrients or food and space availability. So strength, verified the model, R squared's 1, which indicates perfect correlation. Limitation, suitability of the model beyond the data range will be dependent on the resources available to sustain the population, so space and nutrients.